Welcome to this college algebra video on synthetic division and the remainder theorem.
Now, to get us ready to talk about polynomial division and synthetic division, let's go back and review kind of division that we learned back in elementary school. Just long division with numbers. So take just a minute and see if you can, on paper and pencil, do this long division and find out what answer you get. We'll check it in just a minute. Pause the video while you work this out. So now that we're back, I'm going to actually work this problem out here, see if I can remember how to work long division. Boy, it's been so long. I'll have to see if I can recall this. I seem to remember I have to take the 8 and see if it will go into the 7. Well, 8 doesn't go into 7, so I'm not going to put anything up above the 7. But now I'll look and see, does 8 go into 79? Let's see, 8 goes into 79 9 times. I'm going to put a 9 up above that 9. And then I think I multiply 9 times 8. Boy, my elementary school teachers would be proud here. I'm remembering how to do long division. 9 times 8 is 72. So I draw this line under here. And let's see, 79 plus 72 is 151. Wait a minute, now that's bigger than what I started with. Something didn't work right here. Wait a minute, I wasn't supposed to add. I think I was supposed to subtract. So let me mark that here, subtract those. 79 minus 72, sorry elementary school teachers, I'm kind of letting you down here. I'm not remembering how to do this. Let's see, 9 minus 2, that leaves me a 7, and then bring down that 2. 8 goes into 72 9 times. I'm going to put that over the 2. And then 9 times 8 is 72, and 72 plus 72 is 144. Oh, I made that mistake again. I'm not supposed to add these up. I'm supposed to subtract. Just seems like every time I draw that line, I want to add. So let's see, I'm going to draw that line and I'm supposed to subtract. Now 72 minus 72 is 0. 8 does not go into 0, so I'm going to bring down 4. 8 still does not go into 4, so I'm also going to bring down this 5. Oh, but before I just start trying 8 into 45, I have to show that I didn't get anything in this column here. 8 goes into 4 0 times. I'm going to put a placeholder there. Placeholders are very important when we're doing division. We can't just skip over digits. Now, 8 does go into 45. 8 goes into 45 5 times. And beneath that, I'm going to write a 40. And, oh, I almost did it again. I almost drew that line and added them up. I wonder if just every time I would draw that line, I want to add them up. Maybe if I change the sign, draw the line and then change the sign. Hey, that might be a good rhyme to remember that thing. Draw the line, change the sign. Okay, so 45 minus 40, that leaves me with a 5. I'm going to now bring down this 8 because 8 does not go into 5, but 8 can go into 58 7 times. 7 times 8 is 56. Let's see if I can remember now. Draw the line, change the sign. Oh, that'll help me remember not to add, but instead to subtract. And now 58 minus 56 is a 2. I don't have any more numbers to bring down here. So what do I do after this? Well, let's see. I know there were a few different options. Once I learned about decimals, I learned I could put a dot here and a decimal and then some zeros, and I could just keep going, bringing more digits down here. But I want to remember back even a little earlier to this. And I was working on some long division with my daughter, who's in 3rd grade, and she said, when you get down to here, you just say remainder 2. So sometimes you kind of put R, it's 2, remainder of 2. So that maybe was the first way we learned to deal with these when they did not come out exactly even. Remainder 2. There was another way we dealt with these sometimes. Sometimes we would say the answer was 99,057, and we take the 2, our remainder, and put it above the 8. So we could say 99,057 and 2/8, or in reduced form, 99,057 and 1/4. So I guess we have a couple of different ways that we can deal with the remainders. We'll see that there is some similarity now when we go to polynomial long division and what we call synthetic division. So polynomial long division is a process where we're going to divide one polynomial into another. Now, just what we just did, remember, we divided a smaller number into a greater. We always got a quotient and a remainder. Now, sometimes that remainder was 0. We can kind of illustrate that. This is what we did with numbers. A number on the outside, a number on the inside. A goes into B Q times with a remainder of R. And what that really meant was, since division is the inverse operation of multiplication, meant we could take this Q number times A, and if we add the remainder, we can get back to B. So A times Q plus that remainder is equal to B. That's kind of what the results of division mean. Now, when we're going to talk about dividing polynomials, what we're going to want to divide is a smaller degree polynomial into a larger degree polynomial. So our smaller degree polynomial will go on the outside of our division symbol. The larger degree polynomial will go on the inside of our division symbol. The result here, the quotient, is not going to be a number, but the quotient itself will be a polynomial. And sometimes we'll get a remainder, sometimes that remainder will be 0, but if we do get a remainder, that remainder will also be a polynomial. So we've got a polynomial divided into another polynomial. We get a quotient polynomial plus and a remainder polynomial. Now, if we put these back together the same way we think we can with numbers, you can see that d of x times q of x plus that remainder polynomial, r of x, will get you back to the original f of x. All right, let's see some examples of this here. So our first example, the division algorithm, we're going to take a fairly simple polynomial, x minus 2, divided into another polynomial. X minus 2 divided into 6x cubed minus 19x squared plus 16x minus 4. So we're going to kind of follow the same pattern we did just a minute ago. I'm going to look at x minus 2 and say, does it go into 6x cubed minus 19x squared? And really, I'm only going to focus on the beginning of this polynomial and the beginning of this polynomial. Does x go into 6x cubed? Well, sure, I could multiply 6x squared times an x and get 6x cubed. Now, 6x squared tells me that this kind of belongs in this x squared column. I'm going to write a 6x squared up here. And now I'm going to multiply 6x squared times x minus 2. And I'll have to distribute. 6x squared minus x is 6x cubed. 6x squared minus 2 is negative 12x squared. And here's where people sometimes get a little mixed up. They want to add when they get here. Or sometimes they see a minus sign here and they think they're already subtracting. Now, when I draw the line, I change the signs. I kind of use that little rhyme to help me remember and not get my signs all mixed up. I'm going to draw the line and I'm going to change both signs. This is going to become a negative 6x cubed and a positive 12x squared. If I now do addition, because addition is a lot easier to think of than subtraction, 6x cubed and negative 6x cubed add up to 0. Negative 19x squared and positive 12x squared add up to 7x. a negative 7x squared. I'm going to bring down the 16x. It's almost the way I brought down a number that was when I did the numerical division. Now I ask, what times x can give me a negative 7x squared? Well, certainly I've got to multiply times negative 7. I'm going to have to multiply times another x to get up to x squared. So up here in the x column, I'm going to put negative 7x. Negative 7x times x will give me negative 7x squared. That's how I determine this number up here. I'm actually going to multiply negative 7x times the entire quantity x minus 2. So distributing to the x and to the negative 2, we're going to get this. And again, don't just start adding things. We don't want to get a 30x here. We need to draw the line and change the signs. Draw the line, change the signs. This will become a positive 7x squared and a negative 14x. Now it's okay to add. I'll get 0x squared and I'll get 2x. Now we have to decide, does x minus 2 go into 2x minus 4? Well, x goes into 2x twice. I need to multiply x times 2 to get a 2x. I'm going to put that constant value above the constant term. Positive 2 times x is 2x. Positive 2 times negative 2 is negative 4. So when I multiply, I get 2x minus 4. I'm going to draw the line and change the signs. Well, this time when I add up 2x and negative 2x, I get 0. When I add up negative 4 and positive 4, I get 0. So my remainder is 0. All right, what does this tell me? It tells me that if I were to multiply x minus 2 times the polynomial 6x squared minus 7x plus 2, I would get the polynomial 6x cubed minus 19x squared plus 16x minus 4. Here's a quick illustration of what I mean. When I multiply the divisor polynomial times the quotient polynomial, I do get back to the original polynomial that I was dividing, 6x cubed minus 19x squared plus 16x minus 4. Now, this may seem like kind of a chore, sort of difficult to do, keep track of. We're having to write powers of x, keep all of our powers of x lined up, and it seems like it might be a little difficult. With a little bit of practice, though, you can get good at it. We'll do several more examples in this presentation, but I do want to show you a second method of doing division, which you may find to be a little simpler. This is called synthetic division, and it's a shortcut that will work in certain circumstances. Synthetic division is best used if you can write your divisor as x minus k. So x minus a number. If the divisor is ax minus k, or there's a coefficient in front of that x, or maybe a quadratic that you're dividing by, or some higher degree, it's probably better to do long division. There are some modifications we can make to synthetic division to get some of these to work, but for this course, we will do any other kind of division by long division. But let me show you how you can divide the same problem we just did using synthetic division. Here's how we set up synthetic division. Remember, in the old problem, our divisor was x minus 2. I put that 2 kind of outside this little framework. These numbers you may recognize as the coefficients of our old polynomial, 6x cubed minus 19x squared plus 16x minus 4. Well, in synthetic division, we just strip away those powers of x. So I won't put the x cubed, the x squared, the x. I just strip those away. Now here's the process. It's a process of add and multiply. I'm going to add 6 plus whatever's below it. Well, there's nothing below it. 6 plus 0 is 6. So I add when I go down. I'm going to multiply and put my answer diagonally up here. I'm going to take the 2 out here and multiply times 6. 2 times 6 is 12. So I multiplied to get this number down here. Add, then multiply. Now let's repeat the process. Negative 19 plus a 12. When I'm going down, I add. I get a negative 7. When I go diagonal, I multiply. Take the 2 out here times the negative 7. That gives us a negative 14. Add when I go down. 16 plus negative 14 is 2. To go diagonal, I multiply. 2 times the 2 up here gives us a 4. When I go down, I add. Negative 4 plus 4 equals 0. All right, so great. I did this kind of add, multiply process, add, multiply, add, and I got a remainder, or I got this 0. What does all this mean? Well, maybe you recognize the 6, the negative 7, and the 2 as the coefficients of our quotient. 6x squared minus 7x plus 2. Right, going back, 6x squared minus 7x plus 2. So I can take those numbers from my synthetic division and write the quotient as 6x squared minus 7x plus 2. This new quotient will always be 1 degree smaller than the original. Let's try another example here. 3x cubed minus 7x squared plus 2x minus 8 divided by x minus 3. Well, if I were doing long division, I would put x minus 3 on the outside and 3x cubed minus 7x squared plus 2x minus 8 on the inside. But for this, do I have the option of doing synthetic division? I sure do, because what I'm dividing by is x minus k. It's x minus a number. So let's set up synthetic division instead of long division. Outside of my little framework, I put a 3. Inside of the framework, I put 3, negative 7, 2, and negative 8. Those are the coefficients from this polynomial. Now we're going to do our add multiply process. Oops. When I go down, I add. 3 plus 0, because there's nothing to add, is 3. When I go diagonal, I multiply. 3 times the 3 up here is 9. When I go down, I add. Negative 7 plus 9 is 2. When I go diagonal, I multiply. 3 times 2 is 6. When I go down, I add. I'll get 8. When I go diagonal, I multiply. 3 times 8 is 24. When I go down, I add. I got 16. And there's nowhere else to go here. I guess I'm done with this problem, except I need to write what the quotient is. I'm going to take these numbers here, the 3, the 2, the 8, and I'm going to start writing a polynomial. I need to drop my polynomial 1 degree down. So when I divide a cubic function by a linear function, I should drop down to a quadratic function, that is an x squared function. So our quotient, q of x, is 3x squared plus 2x plus 8. And what am I going to do with this number here? This is our remainder. We can write remainder 16. Another option is to write 3x squared plus 2x plus 8 and add 16 over x minus 3. So those are two options of what to do with your remainder. You can either just write the remainder is that number, or take your remainder and write it over the divisor, x minus 3. So those are two expressions that can give me the quotient of this long polynomial divided by x minus 3.
As a second example, let's try the following division. 2x to the fourth minus 3x squared plus x minus 12. That entire polynomial divided by quantity x minus 2. So first thing we need to do is set up our framework for synthetic division. Since we're dividing by x minus 2, I'm going to put a 2 outside of this framework. Now we're going to go through the first polynomial and take all the coefficients to set up the rest of my synthetic division. Well, the coefficient of x to the fourth is 2, but did you notice there's not a term for x cubed? Well, we're going to have to still have a placeholder for x cubed. So we're going to use a 0 as the coefficient for x cubed. Then we can put a -3, a +1, and a -12. So there are all the coefficients set up. That placeholder is an important part of this synthetic division. So now let's start our process. We're going to add and multiply. Add 2 plus nothing, that's 2. Multiply 2 times 2, that's 4. Add 0 plus 4, that's 4. Multiply 2 times 4, that's 8. Add -3 and 8, that's 5. 2 times 5, that's 10. 1 plus 10, that's 11. 2 times 11, that's 22. So finally, this last addition gives us a remainder of 10. So for this problem, our quotient is 2x cubed. Remember, this power is always going to be one step down from the original polynomial we started with. So 2x cubed plus 4x squared plus 5x plus 11 with a remainder of 10.
For our next example, let's divide 2x to the fourth minus 3x squared plus x minus 12, all divided by x minus 2. So remember, our first question is, can we use synthetic division? Well, the thing we're dividing by is x minus 2. It's x minus a number. So I can put that number outside of my little framework here. Looks like this is good, well set up for doing synthetic division. Now remember, these coefficients are going to come down and go inside the framework. Coefficient of x to the fourth is a 2. Now wait a minute. If we look closely here, there is no x cubed term. So we could say that the coefficient of x to the third is 0. And that's going to be important when we do our synthetic division. We want a column for every power of x. So we're going to need a 0 placeholder right here for x cubed. After that 0 placeholder, then we can put the coefficient for x squared as a -3 and the coefficient of 1 for x and the constant -12. So we've got our placeholder and we're ready to proceed with our long division. Let's see how this will come out here. We're going to drop the 2. 2 plus 0 is 2. 2 times 2 is 4. Remember, add when you go down, multiply when you go diagonally. 0 plus 4 is 4. 2 times 4 is 8. -3 plus 8 is 5. 2 times 5 is 10. 1 plus 10 is 11. 2 times 11 is 22. -12 plus 22 is +10. So remember, going down we added, going diagonally we multiplied. And we've got a 2 for our x cubed term. Remember, we have to drop our power down by 1. So this is going to be from degree 4 going down to degree 3. We have a number for our x squared column, plus 4x squared. We have a number for the x column, plus 5x, and we have a number for the constant, plus 11. This last number we've got here, that's our remainder. So we can either write remainder 10, or this quotient 2x cubed plus 4x squared plus 5x plus 11 plus 10 over x minus 2. Taking that remainder and writing it above the divisor. Next example, x to the third minus 2x to the second plus 2x plus 5, all divided by x plus 1. Can we do synthetic division here, or are we stuck with long division? Well, I said that we can do synthetic division when our divisor is in the form x minus a number. Well, wait a minute, x plus 1, is that x minus a number? Well, in fact, it is. We could think of x plus 1 as x minus negative 1. And now this is in a good form for doing synthetic division. Outside of our framework, we're going to put a negative 1. And this is getting familiar when we have using the opposite sign of what we see in a parentheses. When we're dividing by a parentheses, x plus 1. The number that's going to go outside here is the opposite of a positive 1, or a negative 1. Inside the framework, I'm putting the coefficients of x cubed is 1, x squared negative 2, coefficient of x is 2, and the constant is 5. So we're ready to do our synthetic division. Let's get at it. I add, then multiply. 1 plus 0 is 1. Negative 1 times 1 is negative 1. Add and multiply. Negative 3. When I add, negative 1 times negative 3 is positive 3 when I multiply. 2 plus 3 is 5. Negative 1 times 5 is negative 5. 5 minus 5 is 0. Hey, this time we came out with a remainder of 0. So I didn't want to imply from my previous examples that whenever you do long division, you get a remainder, and whenever you do synthetic division, you don't get a remainder, or the other way around. You can get a remainder with synthetic division. You might get a remainder of 0 with synthetic division. It all depends on the division that you started with. Now let's interpret this answer. Remember, our original polynomial was x cubed. I'm going to take a step down and make this 1 the coefficient of x squared. The negative 3 is coefficient of x, and then the 5 is a constant. And we have a remainder of 0, so we don't really have to write the remainder or write 0 over x plus 1. We can simply write our quotient as x squared minus 3x plus 5.